All right, hello. This is Chapter 4, Section 1. Very short. There's only one concept in this section, and that is a probability density function. Now, we've talked about distributions before. That is the values that a variable takes on and how often it takes those values. And we've talked about probability before. Probability has to be between 0 and 1, where 0 is impossible, close to 0 is very unlikely, 1 is absolutely certain, and close to 1 is very, very likely, right? Of course, a lot of times probabilities are not going to be 0 or 1, but something in between, but they cannot be outside of that range. So a probability density function or distribution function has two characteristics. They are, each probability is an actual probability, so this is a probability density function. So each probability has to be between 0 and 1. All the probabilities add up to 1. So if you take all of the values that the variable can take on, their associated probabilities need to add up to 1. Let's take a look at an example. A hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. Let X be the number of times a patient rings the nurse during a 12-hour shift. For this exercise, X is 0, 1, 2, 3, 4, or 5. So if we're thinking about the study, right, they had a random sample of 50 people. Of those 50 people, those 50 patients, the number of times they rang the nurse in the 12-hour shift was 0 times, 1 time, 2 times, all the way up to 5 times. So in all of those 50 people, none of them rang the nurse 6 times or more, right? And a few of them didn't ring the nurse at all. And we have every value from 0 to 5. P of x is the probability that x takes on the value x. And notice we have capital X versus little x, right? So capital X is not great choice of variables from the textbook, but that's okay. Capital X is that variable name, right? And the X values take on these little values here, and P of X is the probability. Is this a discrete probability distribution function? Now, why is it in particular a discrete probability distribution function? Remember, discrete data can only take on certain values, right? So for this one, the patient can't have rung the nurse in the 12-hour shift 4.5 times, right? There's no half time ringing the nurse. You either rang the nurse or you didn't ring the nurse. So the variable can only take on distinct values. Now remember, density doesn't necessarily mean you can't have half values. It just means that you can't have values in between. So in this particular case, the values are whole numbers, but what makes it a discrete variable is that we can't have values between 0 and 1 or 1 and 2 and so on. Okay, so is it a density function? Well, let's see. Are all the probabilities between 0 and, well, it would help if I actually had copied the table to allow us to look at the values, right? So ignore this suppose Nancy one. We'll come back to that. Here, I'll move the Nancy problem further down here. It doesn't distract us. Okay, so here's our table. So we can see our values. Rang the nurse no times, rang the nurse 1 time, all the way up to rang the nurse 5 times. And here's our probabilities, which absolutely did not translate when I copy pasted from the textbook at all. We're looking at it right now, we'd be like, those aren't probabilities. That's definitely much bigger than 1. So let me fix that. We'll just cross these out here. Okay, what are we supposed to have? So the probability that X took on 0. So of the 50 patients, 2 of them rang the nurse no times. 11 of them rang the nurse 1 time. 23 of them rang the nurse 2 times. These aren't lining up very well. I'm not doing a good job of writing them small enough. 9 of them rang the nurse 3 times. 4 of them rang the nurse 4 times. And 1 of them rang the nurse 5 times. So first of all, if these are our probabilities expressed as fractions, how do we know they're between 0 and 1? Well, all of those numbers in the numerator are smaller than 50, right? So if you have a number smaller than 50 and you divide it by 50 or look at it out of 50, that's going to be a decimal smaller than 1, right? What fraction would be equal to 1 with a denominator of 50? That would be 50 out of 50. None of these numerators are 50s, so none of these or more, so none of these are bigger than 1. So that's okay. And of course, if we had a negative number, that wouldn't make any sense, and it also wouldn't be allowed for probabilities. Probabilities are not negative, they're between 0 and 1. So all of those probabilities are between 0 and 1. So we can put a little check mark for characteristic number 1. Now, characteristic number 2. All the probabilities have to add up to 1. So if I do 2 out of 50 plus 11 out of 50 plus 23 out of 50 plus 9 out of 50 plus 4 out of 50 plus 1 out of 50. Let's see. I've got 4 and 1 is 5, so that's 13 out of 50 for these three. 2 and 11 is 13, so I've got 36. Interesting. 36 out of 50. And that is 49. Did I miscount one? Let's see. Because we should expect 50 out of 50. Ah. Hey, y'all. What's 5 plus 9? Is it 13? It's not. You're sitting there like, oh my God, I'm learning math from a guy who can't do 5 plus 9. I would love to tell you that I did it on purpose, but I did not. Well, there you go. Look, see, even people with math degrees can make silly mental mistakes. So now you feel better, right? Yeah, good. Of course. Right. Definitely. Okay, now that adds the 50. And that means that they all sum to 1. So yes, this is a probability density function. Okay, now let's look at that Nancy problem. Suppose Nancy has classes 3 days a week. She attends classes 3 days a week 80% of the time, 2 days a week 15% of the time, 1 day 4% of the time, and no days 1% of the time. Suppose 1 week is randomly selected during the semester, is kind of implied there. Let X be the number of days Nancy attends class. What values does X take on? Well, sometimes she goes every day that week, sometimes she only goes 2 days, sometimes she goes 1 day, and sometimes she takes the whole week off. Not sounding good for Nancy's GPA. Suppose a week is randomly chosen. Construct a probability distribution table and have 2 columns. So we're going to have X. X is the number of days Nancy attends class. The values it takes on are 0, 1, 2, and 3. Notice she couldn't take on, she can't do negative days, and she can't go more than 3 times in a week because there's only 3 classes per week. I suppose in some level you could have half days, right? She might show up for half, but maybe we're saying, by the way, we're categorizing the variable. We say attends class, even if she doesn't stay the whole time. If she shows up, we can call that attends class. So then we don't have half days or more importantly, values in between. So this is a discrete variable. Now, P of X is the probability that X takes on these values. How often does she go no days? Well, that's 1%. As a decimal, what is that? 1. And 1 day she goes 4% of the time. 4 is a decimal. 2 days she goes 15% of the time, 0.15. And 3 days a week, she does pretty good. She goes 80% of the time. Now, all of those probabilities are between 0 and 1. Check. Does it add up to 1? Well, 0.01 plus 0.04 is 0.05. 0.05 plus 0.15 is 0.2. 0.2 plus 0.8 is 1. So yes, this is a PDF. Now, a little sneak preview of us we're going to see in the next section. On a randomly selected week, how often can we expect Nancy to go to class? Well, we do it like this. 0.1% of the time she goes 0 days, plus 0.04% of the time, or not 0.04%, excuse me, 0.04 probability she goes 1 time, 0.15 probability she goes 2 times, and 0.8 probability she goes 3 times. So we're going to multiply these and add them all up, and we're going to get an expected value for Nancy's attendance. This would be a little bit faster if I had typed it on a spreadsheet, but I don't have a spreadsheet pulled up right now, so we're going to do 0.01 times 0, that's going to be 0, right? Plus 0.04 times 1, which is going to be 0.04, plus 0.15 times 2, plus 0.8 times 3. And really, I think you probably could have done this without a calculator, right? Now we get 2.74. Now you might be like, well, wait a minute, Taylor, you said we couldn't have values in between, and we can't have 0.74 of a class. That's true, right? By the way we define the variable, we were saying she either goes or she doesn't, right? She attends or she doesn't, and we don't care how long she's there. But sometimes the expected value or the mean is not actually a value that the variable takes on, right? So when we say 2.74, well, it's closer to 3. It does still give us some information about Nancy's behavior, right? On an average randomly selected week, we can expect her to go 2 or 3 days, but more likely 3 days, closer to 3 days a week. Okay, that's all we have for this section. I'll see you in the next one.